Do you think AI just types? Well, if you still think of artificial intelligence as, a blinking cursor waiting for your text prompt, you are really stuck in the past.
Very true.
Today's AI comes equipped with a 3-sense package. It looks, it listens, and it reads, all at the exact same time.
We are stepping across the threshold into a fundamentally new era of machine intelligence here. I mean, the text-only brain in a jar is becoming an embodied, multi-sensory observer.
Welcome to today's deep dive. Just to set the stage for you, think of me as your AI host. My job is to ask the hard questions, push back on the abstract theories, and make sure we actually understand the mechanisms driving this tech.
And I'll be guiding us through the research as Dr. AI. I'm here to synthesize the data, connect the frameworks, and, break down the complex computer science into the real-world implications we all need to prepare for.
So our mission today is mapping exactly how AI is evolving from that isolated text generator into a true multimodal entity. And to do that, we are tearing into a massive stack of sources. We've got OpenAI's foundational CLIP paper, architectural reviews of Google's Gemini 1.5 Pro, and deep dives into vision language action models.
We're also digging into the mechanics of HMRG and a really comprehensive review on trustworthy multimodal AI.
It's a lot of material.
It is, but it all revolves around one major paradigm shift. Humans naturally use 5 senses to navigate the physical world, right? Our understanding is inherently multimodal.
Exactly.
AI is finally catching up to that, essentially shifting the old idiom from seeing is believing to, well, multi-seeing is true.
Multi-seeing is true. I like that.
Yeah.
Multimodal is definitely the inescapable buzzword in tech right now. But since you, our audience, already know that large language models are incredibly capable at reasoning, coding, and writing, let's skip the basic definitions.
Good idea.
Why is text suddenly not enough? I mean, we've built trillion parameter model that seem to understand the world perfectly well just by reading about it.
Well, they simulate understanding, but they lack physical grounding. A text-only AI doesn't actually know what a cat is.
It just knows the word.
Exactly. It just knows the statistical probability that the word cat appears near the word feline or whiskers. It has a severely impoverished view of reality because, well, the world isn't constructed of text.
Right.
When you restrict a system to text, you force it to understand a dynamic 3-dimensional universe through a tiny keyhole.
Okay, let's unpack this. If an AI only reads text, it's basically like trying to maintain a deep relationship exclusively through text messages or phone calls where you can't see the person's face.
Oh, that's a perfect analogy.
You can read the words, sure,
Okay.
but you completely miss the sarcastic tone, the facial expression, the tension in the room. Misunderstandings are just a mathematical certainty at that point because the contextual data is missing.
Yeah, I mean, consider how much of your own daily decision-making relies on nonverbal cues. You navigate traffic, you read a room before speaking, you assess threats using visual and auditory data simultaneously.
You do it without even thinking.
Right. AI systems have been suffering from this exact same sensory handicap. Bridging that gap really started with giving the machine its eyes.
Which brings us to the first major breakthrough in our sources, the CLIP model, Contrastive Language Image Pre-training.
Yes.
The researchers at OpenAI trained this architecture on 400 million image and text pairs scraped straight from the internet, right?
I did. And the underlying philosophy of CLIP fundamentally changed how we train vision models. Before CLIP, if you wanted an AI to recognize a car, a human had to manually label thousands of pictures of cars.
That sounds exhausting.
It was. It was completely bottlenecked by human labor. CLIP bypassed that entirely by utilizing what we call image embeddings and text embeddings. It takes the mathematical representation of a picture and the math for the words and throws them into the exact same semantic space.
So it's essentially a massive sorting algorithm, like a blind date for data.
Exactly like a blind date.
You have 400 million images on one side, 400 million text captions on the other. The AI plays matchmaker, figuring out which image clusters with which text, pulling matching concepts closer together mathematically and pushing unrelated ones apart.
Yes, birds of a feather flock together, but translated into multidimensional calculus.
But here's where it gets really interesting to me. How does it actually learn this without a human explicitly tagging every single object in those 400 million photos?
So CLIP uses a contrastive objective. It doesn't try to predict the exact words in a caption like older models did. If a picture showed a dog catching a frisbee, older AI would fail if it guessed pup jumping for a toy because the exact words didn't perfectly match the label.
That seems like an impossible standard to train against. There are infinitely valid ways to describe a single photograph.
The researchers realized that. So during training, CLIP is handed a massive batch, say 32,000 images and 32,000 captions all at once.
Wow.
It calculates a huge grid, and its only job is to predict which whole text goes with which whole image out of that specific batch. It's a multiple choice test rather than a fill-in-the-blank test.
That explains the efficiency. But how does that translate to recognizing things it has literally never seen before? If it's just matching things in a batch, how does it achieve what the paper calls zero-shot transfer?
Because the internet is messy and comprehensive. By learning to match 400 million diverse, noisy, real-world examples, it stopped memorizing specific objects and started understanding core visual features.
What do you mean by features?
Like, it learned the concept of fluffy, the concept of orange, and the concept of pointed ears. So when you show it a red panda, even if it never explicitly trained on a red panda label, it can combine those learned features to recognize it. It generalizes.
That is wild. So CLIP successfully maps the static visual world to text. It gives the AI eyes. But a static image is still just a frozen moment in time, right? The real world is dynamic. It's temporal.
Very true.
For a fully multimodal package, we have to talk about audio.
Audio models introduce the element of time and nuance, and the research breaks audio processing into three distinct pillars.
Okay, what are they?
First is speech-to-text, which is just your baseline transcription. Second is the extraction of audio features tracking the pitch, the speed, the cadence. And the third, which is arguably the most complex, is emotion recognition.
That third pillar changes human-computer interaction entirely.
It really does.
I mean, if a human user says, "I'm fine with a heavy sigh, a dropped pitch, and a sharp clip at the end of the word," a text-only transcription bot just logs user state is fine. It completely misses the reality of the situation.
Exactly.
But an audio model catches the sigh, analyzes the pitch drop, and infers this user is definitely not fine.
There is a really fascinating caveat to that in the trustworthy multimodal AI research we reviewed, though. You would think that this nuanced vocal analysis would be the absolute key to building trust between humans and AI.
Right.
But the data reveals something totally counterintuitive.
Wait, really? We trust what we hear less than what we see.
Statistically, yes. When humans interact with an embodied AI or a robotic avatar, facial cues and microexpressions have a significantly stronger influence on our perception of its trustworthiness than vocal cues do.
Oh, wow. That feels deeply wired into human evolutionary psychology. We can easily fake a cheerful tone of voice over the phone, but controlling the micro muscles around our eyes is much harder.
Precisely.
So if an AI wants us to trust it, getting its visual expressions right is marginally more impactful than perfecting the tone of its synthetic voice.
Which really highlights the immense challenge of bringing all these senses together. I mean, we have visual data, auditory data, and text data. They are entirely different formats of information.
Right.
The core mechanism that makes multimodal AI actually possible is a process called alignment.
Let's really dig into alignment, because this seems like the foundational architecture of everything. How do you take the pixels of a dog, the sound wave of a bark, and the letters DOG and force them into the same mathematical brain?
So imagine a master translator. But instead of translating French to English, this translator is converting sensory inputs into a universal machine language.
Okay.
To achieve alignment, the visual cortex, the audio processor, and the text parser all have to arrive at the exact same semantic understanding of a concept.
The source documents talk about encoders and embeddings playing the central role here. We briefly touched on embeddings with CLAP, but let's break down the actual pipeline.
Sure. Every modality has its own dedicated specialist called an encoder. You have a vision encoder analyzing pixel density and color gradients. You have an audio encoder mapping frequency and amplitude.
Got it.
Each encoder processes its specific raw data and compresses it into an embedding.
And just to clarify for everyone listening, an embedding is a highly dimensional vector,
Right.
Just a long string of numbers that represents the core meaning or the concept of that data. I like to think of embeddings as a universal currency. You exchange your visual pesos, your audio yen, and your text euros into this one universal machine dollar. Once it's all in the same currency, the AI can actually spend it and calculate across all of it.
That is a great way to visualize it. The magic of alignment is training the model so that the mathematical vector for the image of the dog is nearly identical to the vector for the sound of the bark.
So they match.
Yes, once those numbers align, the AI is of one mind. It doesn't matter if you show it a picture, play it a sound, or type a word, it accesses the exact same neural pathways.
This universal currency is what allows these models to escape the text box and actually operate in the real world. Let's look at Google's Gemini 1.5 Pro. The architecture reviews highlight a massive 1 million token context window.
It's huge.
For those listening, we need to contextualize what a token actually is in a multimodal system, though.
Right, because in an older text model, a token was basically just a chunk of a word. But in a multimodal model, a token can be a 16 by 16 patch of image pixels or a few milliseconds of audio.
So a 1 million token context window isn't just reading a long book. It means the AI can hold hours of high-definition video, massive audio logs, and thousands of pages of text in its active working memory simultaneously.
Yes, it can ingest a 2-hour movie and instantly cross-reference a specific visual scene with a line of spoken dialogue and a written script you provided.
That native alignment is just staggering. But the implications get even wilder when we move from analyzing data on a screen to controlling physical machines in the real world. This brings us to vision language action models, or VLAs.
This is where we cross into autonomous vehicles and advanced robotics. The AI sees, it reasons using language, and then it actually takes physical action.
But how does that translation actually work? How does a large language model, which is fundamentally designed to output text, physically steer a car?
It maps language reasoning directly to action tokens. So a self-driving car uses its visual encoders to see the 3D space through cameras and LiDAR. It reads a detour sign.
Okay, makes sense.
The language model processes that visual embedding and reasons, the road is closed ahead, I need to merge left. But instead of outputting the English words merge left onto a screen, the model is trained to output numerical action tokens.
And those action tokens are directly hooked into the robotic control APIs, like the steering column angle or the braking pressure.
Exactly. The AI is reasoning through the physical environment using the deep logic of a language model, but executing its decisions through hardware. It treats physical movement as just another modality to be aligned.
That requires an immense amount of real-time processing and context retrieval. What happens when the system encounters a scenario it isn't sure about and needs to actively look for external information to make a decision?
That's a huge challenge.
Right, because if it's dealing with visual and textual data, a traditional keyword search is useless.
This is exactly where the HM-RAG framework comes in. RAG, or Retrieval Augmented Generation, is a well-known technique where an AI searches an external database for facts before answering a prompt, rather than just relying on its training memory.
Sure, we've seen that.
But HM-RAG takes this to an entirely new level. It stands for Hierarchical Multi-Agent Multimodal RAG.
Let's break down the multi-agent part, because instead of one single AI trying to search for everything, this framework deploys a team of specialized subprograms.
Yeah, when you feed this system a complex query, say, you upload a dense engineering diagram of a jet engine and ask it to diagnose a specific stress fracture, a decomposition agent intercepts the prompt.
And what does it do?
It breaks your complex question down into distinct searchable tasks.
Then it dispatches the retrieval agents. And these agents aren't just scanning text documents. They are searching across entirely different types of databases simultaneously.
Right. They query vector databases, which store those mathematical embeddings we talked about, to find visually similar diagrams and related text. And simultaneously, they search graph databases.
We should define that for a second. A graph database doesn't just store data, it maps the relationships between data points. So it understands that Part A physically connects to Part B and requires Tool C for maintenance.
Exactly. And while the agents are pulling from vector and graph databases, they are also searching the live web for the latest maintenance bulletins.
That's a lot of data pulling at once.
It is. Finally, all this raw, multimodal evidence is handed over to a decision agent. This agent evaluates the conflicting data, synthesizes the findings, and generates a cohesive answer.
This architecture solves a massive bottleneck. In older systems, the moment an AI tried to search for information about an image, it would lose the granular connection between the visual diagram and the technical text surrounding it.
Yes, completely lose the context.
But by utilizing specialized agents that can natively read the visual embeddings and text embeddings simultaneously, the context remains perfectly intact.
It is a phenomenal leap in AI reasoning capabilities. But the integration of all these modalities, trained on the open web, leads us directly into the most critical issues raised in our sources, the dark side of multimodal AI.
We really have to talk about the training data here. Because if the foundation of models like CLAP is 400 million unfiltered image and text pairs scraped directly from the internet, well, the internet is not a curated, polite place.
No, it is not.
Aren't we just hardwiring all of human prejudice into the sensory cortex of these machines?
The trustworthy multimodal AI research we reviewed addresses this head-on. The literature confirms that because these models learn from raw, uncurated data, they inherently pick up profound societal biases.
The sources explicitly highlight that vision language tasks, such as automated image captioning, frequently exhibit representational biases regarding protected characteristics like gender, race, and religion.
And we are impartially reporting the data here. The research shows these models inherit spurious correlations. For example, if a model sees thousands of internet images where a specific profession is predominantly associated with a specific gender, the mathematical embeddings align those concepts.
The AI doesn't have a moral compass to know better,
Exactly, it just reflects the statistical distribution of the data it was fed.
which feeds directly into a terrifying technical hurdle, the explainability crisis.
Mhm.
I mean, if an AI is just a massive matrix of billions of numbers, these abstract embeddings we've been discussing, how does it explain its logic to a human?
In tasks like visual question answering or a self-driving car using a VLA model, this is literally a life or death issue.
Yeah.
If an autonomous vehicle makes a sudden, dangerous swerve because it processed a combination of a shadow and a traffic sign, engineers desperately need to know why it made that choice.
We can't accept a black box answer from a machine driving a 2-ton vehicle. The system has to be able to speak our language and audit its own thought process.
The research emphasizes the urgent need for natural language explanations, or NLEs. The goal is to develop secondary mechanisms where the AI can output human-friendly reasoning for its multimodal decisions.
That makes sense.
Furthermore, scientists are utilizing techniques like deconfounded learning to fix those biases we mentioned earlier.
How does deconfounded learning actually work under the hood?
It relies on causal intervention. So let's say a vision model is trained on pictures of snowboards, but 99% of those pictures feature a snowy mountain background. The AI might falsely correlate that snow is what defines a snowboard.
I see.
Deconfounded learning mathematically forces the model to evaluate the object independent of its background context. It breaks the false statistical correlation and isolates the true causal features of the object itself.
It essentially forces the AI to check its own assumptions and separate correlation from causation. That is a monumental mathematical challenge, but absolutely necessary if we are going to deploy these agents into hospitals, cars, and our homes.
We've covered a staggering amount of architecture today.
We really have.
Cool.
Let's distill the journey for everyone. We explored how AI is broken out of the two-dimensional text box. Through the power of alignment, models use specialized encoders to transform visual pixels, audio frequencies, and text characters into the universal currency of embeddings.
Right, and that alignment powers the massive memory windows of Gemini. It allows VLA models to steer physical robots, and it enables the multi-agent teams in HMRAG to research complex real-world problems.
But the data they learn from is messy, carrying inherent biases that researchers are actively fighting to deconfound and explain.
Exactly.
I want you to consider how seamlessly you process the world. You hear a siren, you see flashing lights in your rearview mirror, and you read the speed limit sign, all in a fraction of a second. You instantly synthesize that multimodal data and take action.
It's amazing.
Machines are currently mapping the mathematics of that exact human intuition.
Which leaves us with a final concept to consider. As multimodal AI perfects its ability to simultaneously analyze the microtremors in our voice, track our pupil dilation, and parse the syntax of our words, are we approaching a future where our devices can diagnose our true emotional states with more accuracy than our closest friends and family?
Wow. A machine that knows you are stressed before you even realize it yourself. That is really something to think about.
It really is.
If you are only paying attention to text-generating chatbots, you are missing the revolution. The physical world is not made of text, and neither is the future of intelligence. Thank you for joining us for this deep dive. If you enjoyed unpacking the mechanics behind the headlines, remember to subscribe so you never miss out on our next session. We'll see you next time.